You have watched a soap bubble pop. There one moment trembling and bright and gone the next, too quick to follow. A bubble lasts a few seconds and even that feels brief. Yet deep inside matter, there is a particle that exists for less than a millionth of a billionth of a billionth of a second before it vanishes. It is called the W boson, one of the carriers of the weak force, the force behind certain kinds of radioactive decay. Over the next couple of hours, we will build up to it slowly, one plain step at a time, starting from things you can already picture. If you like taking a single idea apart gently and completely, consider subscribing and stay with me. The question we are chasing is an easy one to ask. Why does something so important die so quickly? The word dying carries a picture, and the picture misleads us here. When something dies, you imagine an ending, a stopping, a body that was here and is now broken into scattered pieces. That picture works for most of the world. It does not work at all for a particle. A particle does not shatter when it dies. Nothing flies apart into smaller leftover crumbs of itself. The particle turns into other particles, lighter ones, and those lighter ones carry away everything that was there to begin with. The first thing is simply no longer present, because it has become something else. This kind of death is a change of identity, not a breaking. Hold on to a simple rule, because the whole story leans on it. In nature, certain quantities are never created and never destroyed. Energy is one. Electric charge is another. When a particle decays, the books always balance. The energy that was there before is thereafter, and the charge that was there before is thereafter. What changes is the form. A single heavy thing becomes 2 or 3 lighter things, and the difference in mass turns into the speed those lighter things fly away with. Think of it less like a cup smashing on the floor, and more like a stack of coins traded for smaller change. You hand over one large coin, and you get back a fistful of small ones. No money has appeared or vanished. The same amount is in your hand, just carried in different pieces. A decaying particle does something close to that, except the large coin does not remain in the pile. It is gone, spent entirely on the small change that flies out. There is one more piece to the rule, and it is the strange one. Mass itself can become motion, and motion can become mass. Albert Einstein gave us the bridge between them, the idea that mass is a frozen, concentrated form of energy. So a heavy particle has a kind of stored wealth simply by being heavy. When it decays, it can spend that stored wealth 2 ways. It can pay for the mass of the new particles it becomes, and it can pay for the speed at which they leave. A heavy parent making light children sends them off moving fast, because there is energy left over after their small masses are covered, and that leftover has to go somewhere. This is why heavy particles tend not to last. A heavy particle is sitting on a fortune of stored energy, and nature, given any chance, prefers to spread that energy into more lighter pieces moving freely. A light particle has little to spend and few cheaper things to become, so it often has nowhere to go and stays as it is. The electron is the clearest case. As far as anyone has ever measured, the electron never decays, because there is no lighter charge thing for it to turn into while keeping the charge books balanced. It is the small change at the bottom. There is nothing smaller to break it into. So when we say a particle dies, we mean it transforms. We mean a moment when one identity ends and others begin, with every conserved quantity passed along intact. Nothing is lost, nothing leaks out of the world. The particle is the candle flame that does not go dark so much as become heat and light and air, carried off in forms you can no longer point to and call by the old name. Keep that one sentence as we go. A particle does not break, it becomes. We will spend the next 2 hours on a single particle that becomes something else faster than almost anything in the known universe. And the first step toward understanding its haste is letting go of the idea that its death is a destruction at all. People met this transformation long before they understood it, and they met it as a sound. A faint, irregular ticking coming from a small box held near a rock or a vial of salt. The ticking is the sound most of us still reach for when we think of radioactivity, and it is the right place to begin. because it is where the world began too. The box is a Geiger counter, named for Hans Geiger, who built the first version with Ernest Rutherford in the early years of the last century. Inside it is a tube of gas. When something invisible shoots through that gas, it knocks electrons loose from the atoms along its path, and that little disturbance becomes a pulse of electric current, and the pulse becomes a click in a speaker. Each click is one invisible thing passing through. The ticking is not the rock making noise. It is the box reporting one by one the particles the rock is throwing out. What strikes anyone who hears it for the first time is the rhythm, or rather the lack of one. The clicks do not come evenly, like a clock. They come in bursts and lulls, fast then slow then fast again, with no pattern you can predict from one click to the next. Hold the counter near a stronger source, and the clicks crowd together into a hiss. Move it away, and they thin out to a lonely tap every few seconds. The rock is not deciding when to fire. It is simply leaking particles at its own steady average, and that average shows up to our ears as something that sounds almost alive. Marie Curie spent years inside that ticking, though she measured it with instruments far more delicate than a clicking box. She and Pierre Curie pulled new elements out of tons of dark ore, radium and polonium, substances so active they glowed faintly in the dark and warmed the air around them. The warmth was the first real clue, the one easy to overlook. A pinch of radium stays slightly warmer than the room around it, all on its own for years, with nothing burning and nothing fueling it that anyone could see. Something inside was releasing energy, quietly and continuously, from a source no chemistry could explain. Here is the everyday picture most people carried then, and many still carry now. Radioactivity feels like a kind of poison, or a kind of fire, a property a material has the way a hot coal has heat, something it does to its surroundings. That picture is worth honouring, because it captures the danger and the energy honestly. But it points outward, at what the rock does to us, when the real story points inward, at what the rock is doing to itself. Set the picture of fire gently aside. The rock is not burning anything, it is not reacting with the air. Deep inside, in the tiny dense cores of its atoms, individual pieces are transforming, one at a time, each transformation flinging out a fast particle that races off and trips the counter. Every click is the death of one of those cores in the sense we just built, a single transformation, a single coin traded for change. The ticking is the sound of identity changing, atom by atom, at a pace no outside force is setting. And that pace is the riddle hiding inside the rhythm. Why does this particular atom transform now, and that one wait 1,000 years? Why does the whole sample keep such a faithful average while no single atom keeps any schedule at all? The counter cannot answer that. It only reports. But the question it raises will follow us all the way to the end, because the particle we are chasing keeps the same kind of clock, only unimaginably faster. To understand its haste, we first have to look closely at one of these transformations and see exactly what turns into what. So let us look closely at the most important of these transformations, the one that sits at the centre of everything to come. It happens to a neutron, one of the two kinds of particle packed into the core of an atom. The neutron is the quiet one, with no electric charge, sitting alongside the positively charged protons in the dense knot we call the nucleus. Inside a stable atom, neutrons can sit there essentially forever. But a neutron left on its own, floating free outside a nucleus, does not last. In about 15 minutes on average, it transforms. Here is what it becomes. The neutron turns into a proton. In doing so, it has to account for electric charge, because the neutron had none, and the proton carries a positive charge. Charge cannot be created from nothing, so at the same instant the neutron also throws out an electron, which carries an equal negative charge. Add the new proton's positive charge to the ejected electron's negative charge, and they cancel exactly to zero, which is what we started with. The book's balance. That ejected electron is the fast particle that trips the counter. For historical reasons, an electron flung out of a nucleus this way got the name beta particle. from the early days when scientists sorted the rays coming off radioactive material into 3 kinds and labelled them with Greek letters: alpha, beta, gamma. The beta rays turned out to be ordinary electrons moving fast. So this whole process, a neutron becoming a proton and ejecting an electron, is called beta decay. It is the engine behind a great many of those clicks. You can picture the neutron as a sealed container that, given enough time, rearranges its insides and converts into a slightly lighter container, paying for the change by spitting out a small fast object. The neutron is a touch heavier than the proton, just barely, and that small surplus of mass is the stored wealth we talked about. It funds the whole transaction. It pays for the electron's small mass and gives the electron and proton their speed. Nothing is wasted and nothing is conjured. This single move, neutron to proton, is one of the most consequential in all of nature, even though it looks modest. It is how one chemical element can become another. A nucleus with a certain number of protons is a certain element. Add a proton by turning a neutron into one, and the nucleus has climbed one step up the ladder of elements, becoming something new with new chemistry. Beta decay is one of the ways the universe shuffles the deck, building heavier elements and reshaping lighter ones, inside stars and inside the rocks beneath your feet. It is worth sitting with how strange the calm of it is. There is no violence we can point to, no collision, no trigger. A free neutron simply waits, and then, at some unpredictable moment, it converts, as if a hidden coin somewhere inside it had finally come up the right way. The transformation is clean and complete. One instant there is a neutron, the next there is a proton and a receding electron, and the neutron is not broken into a proton piece and an electron piece. It has become them, fully, in the sense we built earlier. The electron was not hiding inside the neutron the whole time, waiting to be released. It is made fresh in the moment of decay, paid for out of the neutron's stored mass. For a while, this looked like a complete and tidy picture. Neutron in, proton and electron out, charge balanced, energy balanced. 2 particles before, 2 particles after, the whole thing closed and accounted for. It was tidy, and it was wrong. When physicists measured the energy those electrons carried away, the books that had seemed to balance so cleanly stopped balancing at all. The trouble showed up in a graph, and it is worth understanding exactly what the graph said, because the puzzle it posed nearly broke the principle physicists trusted most. The measurement was simple to describe. Take a source that undergoes beta decay, catch the electrons it flings out, and measure how much energy each one carries. Then count how many electrons come out at each energy and plot it. You're asking a plain question. When a neutron turns into a proton and an electron, how fast does the electron leave? By the tidy picture we just built, the answer should be a single number. Every neutron is identical to every other neutron. Every proton is identical to every other proton. The mass that disappears in the transformation is always the same, so the leftover energy should always be the same, and the electron should always carry away the same fixed amount, because it is the only thing left to carry it. The graph should show a single sharp spike at one energy, and nothing anywhere else. That is not what the graph showed. Instead of a spike, there was a smear. The electrons came out with all sorts of energies, from almost nothing up to a maximum, spread across the whole range in between. Some left slowly, some left fast, most left somewhere in the middle, and the few that left at full speed reached an energy that matched what the tidy 2-body picture predicted. But almost all the others fell short, sometimes far short, as if part of the energy they were owed had quietly gone missing on the way out. This was a genuine crisis, not a measurement quirk. Energy conservation is not a rule physicists are willing to bend casually. It is one of the deepest regularities in all of science, tested 10,000 ways and never once caught failing. Yet here was a process where the energy coming out seemed to depend on luck. Run the decay once, and the electron might carry the full amount. Run it again, and the electron carries half, with the other half nowhere to be found. The proton recoils a little, but nowhere near enough to absorb the difference. The energy was simply, repeatably, not all there. Niels Bohr, one of the founders of the whole quantum picture of the atom, took the crisis so seriously that he was willing to consider the unthinkable. Perhaps, he suggested, energy is conserved only on average, across many decays, and not in each single one. Perhaps at this smaller scale, the strict bookkeeping we trusted simply does not hold, and energy can run a little short here and a little long there, balancing out only in the crowd. Coming from Bohr, this was not a careless thought. It was a measure of how seriously the data threatened the foundations. To feel the unease, imagine paying for the same item at the same shop every day, and being charged a different amount each time, with no pattern, the receipts never matching the price on the shelf. Either the price is not fixed, or money is leaking out of your wallet through a hole you cannot find. Bohr was prepared to say the price was not fixed. The alternative, that something invisible was slipping out of the wallet, seemed almost as wild. The spread of energies had a clean shape too, which made it harder to wave away. It was not random noise. It was a smooth curve, rising and falling in a definite way, with a firm upper edge exactly where the tidy picture said the electron's energy should land. That firm edge was a clue. It said the full energy was available, and the electron simply usually failed to take all of it. Something else, present in every decay, was taking a variable share and carrying it off unseen. But nothing else had ever been detected leaving the nucleus. The puzzle was not a missing amount, it was a missing thing. Into that crisis stepped Wolfgang Pauli, and the way he stepped in tells you something about how hard the choice felt. Pauli was one of the sharpest minds of his generation, famous for a tongue so critical that a wrong idea brought to him rarely survived the conversation. He was not a man who proposed things lightly, and what the missing energy seemed to demand was, by his own lights, almost too much to ask. The logic backed him into a corner. If energy really is conserved in every single beta decay, and the electron usually leaves with less than its full share, then something else must be carrying the rest away. That something has to be present in every decay. It has to be able to take any amount of energy from nearly nothing up to the maximum, which is why the electron's energy varies. And it has to be completely invisible to every instrument anyone had, slipping out of the experiment without leaving a single trace. The only way to save the most trusted law in physics was to invent a new particle to order, built precisely to fit a hole no one could see into. So in 1930, Pauli wrote a now famous letter to a meeting of physicists he could not attend, addressing them with a wink as the radioactive ladies and gentlemen. In it he proposed exactly that desperate measure, a new, tiny, neutral particle, born in each beta decay, carrying away the missing energy. To balance the books, it had to be electrically neutral, so it would not show up as a charge anywhere. It had to be very light, perhaps with no mass at all, and it had to interact with matter so feebly that it could pass through the whole apparatus, and indeed through the whole Earth, without touching anything. That last requirement is what troubled him. Pauli understood that a particle which interacts with almost nothing is a particle you may never be able to detect, even in principle. And there is an old, sound rule in science that you should be wary of proposing things you can never test. To save a law by inventing an undetectable particle felt dangerously close to saving it by inventing an excuse. He is said to have confessed in his unease that he had done a terrible thing, postulating a particle that could not be found. It helps to feel the shape of the gamble. Imagine balancing a household budget where the numbers never quite add up, always a little short. You have two choices. You can decide that money simply is not conserved, that some nights it quietly evaporates, which throws out the whole idea of accounting. Or you can insist the accounting is sound and conclude there must be a silent expense you have never managed to catch in the act, a draft under a door you cannot find. Pauli bet on the silent expense. He chose to trust the law and pay for that trust with a ghost. It was a conservative gamble dressed as a wild one. By inventing a new particle, Pauli was actually defending the old deep principles. He would rather expand the list of things that exist than abandon the rule that energy is never lost. Bohr's path, giving up strict conservation, looked more cautious because it added nothing new, but it cut far deeper because it loosened a law the whole structure of physics rested on. For a few years the ghost stayed a ghost, a clever bookkeeping entry with no name and no theory behind it, defended by one man's faith in conservation. It needed someone to take it seriously enough to build it into real, working physics, to give it a name and a place in the equations, that someone was about to arrive, and he would do far more than name it. The man who took the ghost seriously was Enrico Fermi, and he was the rare physicist who was brilliant at both ends of the work, the abstract theory and the hands-on experiment. Where Pauli had floated an idea in a letter, Fermi sat down and built it into a complete working theory of how beta decay actually happens, equations and all. In doing so, he gave the new particle the name it still carries, and he gave the world its first real grip on a brand new force of nature. The name came first, and it came with a touch of humour. By the early 1930s, James Chadwick had discovered the actual neutron, the heavy neutral particle in the nucleus, and that word was now taken. Pauli's hypothetical particle was also neutral but tiny, almost nothing at all. Fermi, who was Italian, called it the neutrino, which in Italian means roughly the little neutral one. The neutron was the big neutral one in the nucleus. The neutrino was its featherweight cousin, the little neutral one that fled the scene. The name stuck, and it fit, because as far as we can tell, the neutrino is almost unimaginably light, far lighter even than the electron. Then Fermi did the harder thing. In 1933 and 34, he wrote down a theory of beta decay that treated the whole event as a single point-like happening. In his picture, a neutron sits there, and then, all at once, at one spot it converts. Out come a proton, an electron, and one of Pauli's neutrinos, all created together in that instant. The electron and the neutrino were not hiding inside the neutron beforehand. They were made fresh, conjured at the moment of decay out of the available energy, exactly the kind of transformation we built up earlier. Fermi's equation said how often this would happen, and predicted the smeared spread of electron energies that had started the whole crisis, because now two light particles, the electron and the neutrino, shared the leftover energy between them in varying proportions. The deeper gift in Fermi's work was the recognition that this required a new force. The transformation he described could not be done by gravity, which is far too weak and only pulls. It could not be done by electricity and magnetism, which act between charges and could not turn a neutron into a proton. And it could not be done by the strong force that glues the nucleus together, because that force does not change one kind of particle into another like this. Beta decay demanded its own distinct interaction, with its own strength and its own rules. Fermi's theory was the first description of what we now call the weak force, or the weak interaction. He even captured its strength in a single number, now called the Fermi constant, which measures how feebly this force acts, and feeble is the word. The weak force is the reason a free neutron takes a leisurely 15 minutes to decay rather than a flicker of a second. It is the reason the neutrino can sail through the entire Earth without noticing it is there. The same faintness that made Pauli despair of ever detecting the neutrino is built right into the constant Fermi measured. The force is real, but it is shy. Fermi was so confident in his theory that he submitted it to a leading journal, which famously rejected it as too speculative and too far from reality. He was undeterred, published it elsewhere, and within a few years it had become the backbone of the field. The neutrino itself would not be caught red-handed for more than 2 decades, but Fermi's equations worked so well that few doubted it was there, and yet his beautiful theory carried a flaw inside it, hidden at low energies and ruinous at high ones. Pushed hard enough, Fermi's point-like force predicted something impossible. The flaw in Fermi's theory was invisible at the gentle energies of ordinary radioactivity, and that is exactly why it stayed hidden for a while. To see it, you have to imagine pushing the weak force much harder than a decaying rock ever does, smashing particles together at high speed and asking how often the weak interaction makes something happen. When physicists worked that out from Fermi's equations, the answer climbed and refused to stop. Here is the heart of the problem, kept in plain terms. Fermi had modelled beta decay as a single point-like event, everything happening at one spot in one instant, the neutron touching its fate directly and converting. That picture is simple, and it works wonderfully at low energy, but the strength of the interaction in his theory grew with the energy of the particles involved. The faster and harder you made them collide, the more likely the weak force was to act, with the probability rising in step with the energy, on and on without limit. The trouble is that a probability is not allowed to do that. A probability is a fraction of 1. Something either happens or it does not, and the chance of it happening can run from 0, never, up to 1 certainly, and not a hair beyond. You cannot have a 200% chance of an event. It is meaningless. Yet Fermi's theory, taken at face value and pushed to high enough energy, predicted exactly that. Chances that sailed past 100% and kept rising, as if an event could be more than certain to occur. When a theory predicts a probability greater than 1, it is not making a daring claim. It is announcing its own breakdown. It is telling you, in the clearest language physics has, that it has been pushed past the place where it makes sense, and that it cannot be the final word. Something in the picture must be wrong or missing, something that only matters at high energy, and that gently caps the runaway before it becomes absurd. At low energy, that missing piece hides, because the runaway has barely begun. At high energy, it has to step in. Think of it like a map drawn for a single town. Within the town, the map is perfect, every street in its place. But the map maker drew the streets as if the earth were flat, which works fine across a few miles. Try to use that same flat map to chart a path across an ocean, and it falls apart, distances stretching into nonsense because it left out the curve of the world. The curve did not matter in town. It matters across an ocean. Fermi's theory was a flawless town map of the weak force that quietly assumed a flatness, which only failed once you travelled far enough. So the very success of Fermi's theory pointed past itself. Its point-like simplicity, the idea that the neutron just touches its transformation directly with nothing in between, was the source of the runaway. A truly point-like force, acting at zero distance with no go-between, was too blunt an instrument. The probabilities it predicted grew without restraint because there was nothing in the model to soften the blow at high energy. What was needed was a go-between. If the weak force were not a direct touch, but were instead passed along by some intermediate particle, a carrier that lived briefly between the neutron and its products, then the math would change. That carrier could rein in the runaway, smoothing the rising probability back below 1 where it belonged, fixing the flat map error by adding the missing curve. The fix, in other words, was to stop treating the weak force as a touch and start treating it as a message sent from one particle to another by a courier. That idea that forces are carried by particles passed between things is one of the most powerful in all of physics. To see where the weak force's missing courier came from, we first need to meet the courier we understand best. The clearest example of a force carried by a particle is the one you're using right now to read these words: light, and the electric and magnetic forces behind it. Step back from the weak force for a moment and look at electricity and magnetism, because physicists understood these first, and the picture they built there became the template for everything else, including the missing courier we are hunting. Start with the everyday picture of a force, the one we all carry. A force is a push or a pull that one thing exerts on another across the space between them. Two magnets snap together or shove apart. A comb run through your hair lifts a scrap of paper from a distance. The Earth holds the Moon without any rope between them. In each case, it feels as though influence simply reaches across empty space, instant and direct, one object tugging another with nothing in between. Honour that picture, because it describes what we see, then set it aside, because the deeper story is stranger and more beautiful. In the modern view, nothing reaches across truly empty space on its own. When two electric charges push on each other, they do it by exchanging particles of light, called photons. One charge sends out a photon, the other absorbs it, and the act of sending and receiving is the push or the pull. The force is not a mysterious reach across the gap. It is a constant, rapid handoff of tiny messengers flying back and forth, each one a packet of the electromagnetic field. The photon is the courier of electromagnetism. A homely comparison helps, as long as we are honest about where it fails. Picture two people on ice skates throwing a heavy ball back and forth. Each time one throws the ball, the throw shoves them backward. Each time the other catches it, the catch pushes them back too. From a distance, with the ball too small to see, it would look as though the two skaters simply repelled each other across the ice, pushed apart by an invisible influence. The ball is the messenger, and the throwing and catching is the force. That is roughly how a repulsive force works through exchange particles. The comparison breaks down at attraction, and it breaks down in a way worth noticing because the breakdown is where the real physics lives. Throwing a ball can push two skaters apart, but it is hard to see how it could pull them together. Yet electric charges attract as easily as they repel. Opposite charges draw close. To make exchange explain attraction, you have to leave the skating rink behind and trust the equations, which handle attraction and repulsion alike through the same exchange of photons. The picture got us in the door. The math carries us the rest of the way, as it so often must. The photon has a few features worth holding on to, because soon we will meet a courier that differs from it in one crucial respect. The photon has no mass. It is a particle of pure energy and motion, and a massless courier can travel any distance at all. That is why the electric force, and gravity too, reach across the entire universe, fading with distance but never truly stopping. Starlight crosses billions of years of empty space to reach your eye precisely because its courier weighs nothing and tires of nothing on the way. This whole framework, forces as the exchange of carrier particles, grew into one of the most precisely tested theories ever built, the quantum theory of light and matter. It got the template exactly right for electromagnetism. The natural thought was that every force should work this way, each with its own courier. The strong force has its couriers. Gravity, we suspect, has one we have not yet caught, and the weak force, the one that needed saving from Fermi's runaway, must have couriers of its own. The question was what kind, and the answer turned on the one feature the photon does not have. The one feature the photon lacks is mass, and that lack is exactly the lever that explains the weak force's courier. To pull on this lever, we have to ask a question that sounds almost too simple. Why does the electric force reach across the whole universe, while the weak force reaches no farther than the inside of an atomic nucleus? The same exchange of couriers idea should govern both. So why are their ranges so wildly different? The answer, worked out in the 1930s by the Japanese physicist Hideki Yukawa, ties the range of a force directly to the mass of its courier. Yukawa was thinking about the strong force that holds the nucleus together, not the weak one, but the logic he uncovered is general, and it is the key we need. His insight was that a massless courier gives a force of infinite reach, while a heavy courier gives a force that dies away over a very short distance. The heavier the messenger, the shorter the leash. To feel why, we need one strange and genuine rule of the quantum world, which we will meet more carefully later but can borrow now. Nature allows a kind of brief, borrowed existence. A particle can flicker into being for a fleeting instant, carry a message, and vanish, as long as it pays back what it borrowed quickly enough. These flickering couriers are sometimes called virtual particles because they live on borrowed time and are never directly seen. The photon between two charges is one of these. It is conjured, crosses the gap, and is absorbed, all in a borrowed moment. Here is the crucial part. To conjure a courier, you have to borrow at least enough energy to make its mass, because mass is stored energy, as we said. A massless photon costs almost nothing to conjure, so it can be borrowed very generously and travel very far before the debt comes due. But a heavy courier costs a great deal to bring into being, and the more you borrow, the faster nature demands it back. A heavy messenger can therefore exist only for the briefest flicker, and in that flicker it can cross only a tiny distance before it must be repaid and disappear. Its heaviness keeps it on a short leash, and so the force it carries cannot reach beyond that leash. So range and mass are two faces of one fact. A long-reaching force, like electricity, must have a light, ideally massless courier. A short-reaching force, like the weak interaction, must have a heavy one, and the weak force is short-reaching to an extreme degree. It does its work only when particles are practically on top of one another, within a distance far smaller than a single atomic nucleus. By Yukawa's logic, that minuscule range demands a courier that is not just heavy but enormously heavy, far heavier than the proton, far heavier than anything found in an ordinary atom. This is a beautiful turn, because it converts the puzzle of Fermi's runaway into a prediction. Fermi's theory failed because it treated the weak force as a direct touch at zero distance. Replace that touch with the exchange of a very heavy courier, and the force naturally acquires its tiny range, and the high-energy runaway is reined back in. The same heavy particle that gives the force its short leash also caps the runaway probabilities below 1, where they belong. One new particle, if it is heavy enough, solves both problems at once. The courier even earned a name before it was found, a plain and honest one, the W boson, the W standing for weak. By the logic of range and mass, it had to be a heavyweight, a single particle weighing as much as a small atom, conjured for the briefest instant to carry the weak force across a gap narrower than a nucleus. Predicting it was one thing. Building the full theory that demanded it, and naming its companions took 3 more physicists and a daring leap. The full theory that demanded the W came from 3 physicists working partly together and partly apart, and the leap they made was bolder than just predicting a heavy courier. Sheldon Glashow, Stephen Weinberg and Abdus Salam took the weak force and the electric force, which look nothing alike in everyday life, and showed they are 2 expressions of a single deeper force. Their work is called the electroweak theory, and it reshaped how we understand the forces of nature. On the surface, the 2 forces could hardly seem more different. Electricity and magnetism are familiar, reach across the universe, and are carried by the massless photon. The weak force is feeble, hides inside the nucleus, and shows itself only in slow radioactive decay. To claim these are the same force is like claiming that ice and steam are the same substance, which of course they are, water in 2 faces. The electroweak idea says the weak and electromagnetic forces are likewise one thing wearing 2 faces, looking different only because of the conditions we happen to live in. Glashow laid important groundwork in the early 1960s, fitting the weak and electromagnetic forces into a single mathematical frame. Weinberg and Salam, working independently a few years later in the late 1960s, sharpened the picture and added the crucial ingredient that gave the carriers their masses, which we will come to shortly. The 3 did not sit in one room dividing the labour. They built overlapping pieces of the same structure over several years, and the field eventually saw that the pieces formed one coherent whole. The theory made a bold and specific prediction, and this is what matters most for our story. If the weak and electromagnetic forces are truly unified, then the weak force needs not one courier but a small family of them, cousins to the photon. There had to be 2 carriers of electric charge, one positive and one negative, which we call the W boson in its 2 forms, the W plus and the W minus. And there had to be a 3rd electrically neutral carrier, heavier still, which they named the Z boson. The photon, massless and far-reaching, was the 4th member of the family, the one we'd known all along. The W bosons explained beta decay directly. When a neutron turns into a proton, it does so by briefly emitting a W minus, which then converts into the electron and the neutrino that fly out. Fermi's single point-like event was really this 2-step relay, with the heavy W as the courier in the middle, conjured for an instant and gone. The runaway in Fermi's theory was tamed exactly as Yukawa's logic promised, because the heavy W gave the force its short range and capped the probabilities. The Z boson was the genuinely new prediction, the part that had not been seen in any decay. It carried no charge, so it could let particles interact through the weak force without changing one kind into another, a quiet nudge rather than a transformation. This kind of interaction, called a neutral current, had never been observed because no one had known to look, when experiments at the great European laboratory found exactly that kind of weak interaction. In the 1970s, it was a stunning confirmation that the theory was on the right track, years before the W and Z themselves were caught. For this work, Glashow, Weinberg and Salam shared the Nobel Prize in 1979, several years before the particles they predicted were actually found. The theory was that convincing on its own, but it carried a deep contradiction at its heart, a problem so severe it had nearly sunk the whole approach. The math that unified the forces insisted the carriers be massless, like the photon, yet the W and Z plainly had to be heavy. Both could not be true, and resolving that clash required one of the strangest ideas in modern physics. The contradiction was sharp enough to deserve its own careful look, because for years it stood in the way of the whole electroweak idea. The problem was this: the beautiful mathematics that unified the weak and electromagnetic forces had a deep symmetry built into it, a balance among the four carriers that made the equations work and tamed the high-energy runaways. But that very symmetry demanded that all four carriers be massless, weightless, every one of them like the photon. The math would only stay consistent if the W and Z weighed nothing at all. Reality said the opposite and said it loudly. We already knew from the weak force's tiny range that its couriers had to be enormously heavy. By Yukawa's logic, a massless W would carry a force reaching across the universe, like electricity, and the weak force plainly does not. It hides inside the nucleus, so the carriers had to be heavyweights. The theory wanted them weightless. The world insisted they were heavy. This was not a small discrepancy to be smoothed over. It was a flat contradiction at the foundation. You could try the obvious thing, which is simply to write a mass for the W and Z into the equations by hand to insist on it. Physicists tried. The result was a wreck. The moment you forced a mass onto the carriers directly, the careful symmetry that made the theory work collapsed, and the high-energy runaways came roaring back, the probabilities greater than one disease returning in full. A blunt, hand-inserted mass broke the very machinery that had made the unification beautiful and consistent. The theory was only well behaved when its carriers were massless, and it was only true to the world when they were heavy, and there seemed no way to have both. It is worth sitting in this bind because it is a familiar shape in physics and in life. You have a principle that is elegant and powerful, but seems to contradict plain fact. The temptation is to abandon the principle. The harder and often better path is to ask whether the principle can be kept, while the contradiction is dissolved by some new ingredient nobody had thought to add. Pauli had faced this with energy conservation, and chosen to add a particle. Here the choice was the same in spirit, but the addition needed was far stranger. The way out when it came was to keep the symmetry in the underlying laws but let it be hidden in the world we actually live in. The idea is called spontaneous symmetry breaking, and the everyday version is easy to picture. Stand a pencil perfectly on its point. The situation is perfectly symmetric. No direction around the pencil is special. Every way it might fall is equally likely. But the pencil cannot stay balanced. It topples, and the instant it does, it picks one direction, and the lovely symmetry is gone from the result, even though it was perfect in the setup. The laws were symmetric. The outcome is not. The thought then was this: perhaps the laws of the electroweak force are perfectly symmetric, with all four carriers massless in the deep equations, just as the math demands. But perhaps the universe we live in is like the toppled pencil, settled into one particular state that hides that symmetry. And perhaps, in settling, something switches on that gives the W and Z their mass while leaving the photon weightless, so the symmetry survives in the laws but is broken in the world. For that to work, there had to be something filling all of space, something the carriers could push against to gain their weight, present everywhere, and the same everywhere, the thing the toppled universe had settled into. That something is a field, and it is the next piece of our story. That something filling all of space is now called the Higgs field, and it is worth meeting plainly, because around it has grown more mystique than almost any idea in modern physics. Stripped of the drama, the Higgs field is a kind of invisible substance that exists everywhere, in every cubic inch of the universe, with no empty spot anywhere free of it. It has been there since the early universe settled, like that toppled pencil, into the state we now live in. And its job, for our purposes, is simple. It is the thing the W and Z bosons push against to become heavy. The idea was worked out in 1964 by several physicists at once, including Peter Higgs, whose name ended up attached to it, along with François Englert and Robert Brute and others, who arrived at the same insight independently. They were not thinking about the weak force in particular. They were solving the general puzzle of how a carrier particle could gain mass without wrecking the symmetry of a theory. Their answer was that if a field of the right kind fills all of space and has settled into a non-zero value everywhere, then particles moving through it can be slowed by their interaction with it, and that sluggishness is exactly what we measure as mass. Here is the everyday handle, and it has a famous failing we should be honest about. Picture the Higgs field as a thick invisible syrup filling all of space. A particle that interacts strongly with the syrup is like a swimmer who drags heavily through it, hard to get moving and hard to stop, and that resistance is its large mass. A particle that barely interacts slips through almost freely, like a swimmer in open water, and that lightness is its small mass. A particle that does not interact at all, like the photon, glides through as if the syrup were not there, and so it stays massless and races at full speed. The comparison gets the spirit right and one detail wrong, so hold it loosely. Real syrup slows a moving object more the faster it goes and brings it to rest. The Higgs field does not drag like that, and a heavy particle once moving keeps moving. Mass is better thought of as the difficulty of changing a particle's motion, the stubbornness it shows when you try to speed it up or turn it, not a continuous friction. The syrup picture captures why some particles are heavy and others are not. It fails on the mechanics, and that is fine, because the math beneath it does not fail. What matters for our story is the punchline. The W and Z bosons interact strongly with the Higgs field, dragging heavily through that universal medium, and so they emerge as very heavy particles. The photon does not interact with it at all, and stays massless, which is why electricity reaches across the universe, while the weak force stays trapped inside the nucleus. The same field gives both their character. The contradiction is dissolved. The deep laws keep all four carriers massless and symmetric, but the field fills space and breaks that symmetry in the world we live in, handing mass to 3 of the 4. There is one more reward in this idea, and it is the part that made the whole thing testable. A field that fills space should, if you strike it hard enough, ring like a bell, and that ringing would itself be a particle, a ripple in the Higgs field. That particle is the Higgs boson, and finding it would prove the field was really there. It took nearly 50 years and the largest machine ever built, but in 2012 the Higgs boson was finally found, confirming that the invisible field is real, and that this is genuinely how the W gets its weight. Now we can put a number on just how heavy the W boson is, and it is worth dwelling on, because that heaviness is the secret engine behind its swift death. The W boson weighs about as much as 85 protons. Let that settle. A single one of the weak force's couriers, a particle smaller than an atom in every meaningful sense, carries the mass of 85 of the protons that make up ordinary matter. To feel the strangeness, hold the proton itself in mind first. A proton is already a substantial little object on the scale of particles. It is what sits at the heart of a hydrogen atom, the most common kind of matter in the universe. Nearly all the weight of everything you have ever touched comes from the protons and neutrons in the nuclei of its atoms, and a neutron weighs almost exactly the same as a proton. So when you lift a stone, you're essentially feeling the combined weight of an unthinkable number of protons and neutrons. The proton is the standard coin of mass in the everyday world. Now stack 85 of those coins into one particle. That is the W boson. It is not a composite thing built of 85 protons glued together. It is a single, indivisible particle that simply happens to carry that much stored energy as mass. Physicists measure such masses in units of energy, because mass and energy are the same currency, and the W comes in at about 80 billion of those energy units, against the protons roughly 1 billion. The ratio is what we should hold on to. 1 W weighs as much as 85 protons, give or take. There is a quiet wonder in where that mass comes from. The W does not have its weight built in from the start. In the deep symmetric laws, it is massless, like the photon. Every ounce of its 85 proton heft comes from how strongly it drags through the Higgs field that fills space. The W interacts with that field about as fiercely as anything we know, and the field loads it down accordingly. Its mass is a measure of its grip on the invisible medium it swims through, nothing more and nothing less. This heaviness is the source of everything strange about the W, and it pulls in two directions that will matter greatly later. On one side, the great mass is why the weak force is so short-ranged and so feeble. Recall Yukawa's logic. A heavy courier can be conjured only for the briefest flicker, and can cross only the tiniest distance, so the force it carries cannot reach beyond the inside of a nucleus. The W's 85 proton mass is precisely why the weak force barely reaches at all, why a free neutron dawdles for 15 minutes before decaying, why neutrinos slip through the Earth untouched. On the other side, and this is where we are headed, that same great mass is why the W, once it does come into real existence, dies almost instantly. A heavy particle is sitting on an enormous fortune of stored energy, and nature, as we said at the very beginning, seizes any chance to spread such a fortune into lighter pieces flying free. The W's 85 proton mass is a vast purse of energy, with countless cheaper things to be spent on, and the spending happens at terrible speed. The same heaviness that makes the weak force shy makes the W boson short-lived. These are not two facts but one, seen from two sides. Before we can measure that swift death though, the W had to be caught in the act of existing as a real particle, not just a fleeting virtual courier. Conjuring a particle that heavy, even for an instant, takes a tremendous concentration of energy, more than any natural process near us provides. To make a real W, physicists had to build a machine that could pack that much energy into a single collision, and then they had to perform a near impossible trick to make the collisions happen at all. To make a real W boson, not the fleeting virtual courier inside a decay, but a genuine particle that exists on its own for a moment, you have to gather in one tiny spot more energy than 85 protons worth of mass, and you have to do it fast. The place this was achieved was the great European laboratory near Geneva called CERN in the early 1980s, and the people who led it were Carlo Rubbia and Simon van der Meer, two men as different as their talents. Rubbia was the force of will, an Italian physicist famous for his intensity and his impatience, the kind of leader who pushed people and machines to their limits and sometimes past them. He had a bold plan. CERN had a large ring that could accelerate protons to tremendous speeds. Rubbia's idea was to send protons one way around the ring, and antiprotons, the antimatter mirror of protons, the other way, and crash them head-on. When matter and antimatter meet, they annihilate completely into pure energy, and that concentrated energy could now and then congeal into a heavy W or Z. It was the most efficient way known to pack enough energy into one spot. The plan had a brutal practical problem. Antiprotons do not exist lying around to be scooped up. You have to make them, one painful collision at a time, and when you do, they come out in a wild, spreading, disorganized swarm, flying off in slightly different directions with slightly different speeds, like a cloud of gnats. To collide them with protons usefully, you need them gathered into a tight, orderly, fast-moving beam. A loose swarm of antiprotons will almost never hit anything. The collisions you need simply will not happen unless the swarm is first tamed into a disciplined stream. This is where Simon van der Meer comes in, the quiet engineer's mind to Rubbia's fire. Van der Meer, a Dutch physicist, had invented a remarkable technique for taming such a swarm, called stochastic cooling. The word cooling is used because a hot gas is one whose particles move every which way at varied speeds, while a cold one is calm and orderly. Van der Meer's trick made the antiproton swarm colder in exactly that sense, squeezing the randomness out of it until the particles march together. The method itself is almost unbelievably clever. As the swarm of antiprotons circles the ring, a sensor on one side watches a clump of them and notices, say, that they are drifting a little too far to the left. It sends a signal straight across the ring, taking the short path through the middle, while the antiprotons take the long way around the curve, so the signal arrives first. A device on the far side then gives that clump a tiny, precisely timed nudge back towards center as it arrives. Do this thousands of times a second, watching and nudging, and the wild swarm slowly settles into a tight, cold, orderly beam, ready to be collided. The signal racing across the diameter to beat the particles around the rim is the heart of the trick. It is worth picturing the patience in it. Stochastic cooling does not grab the whole swarm at once. It corrects tiny samples over and over, each nudge almost too small to matter, the order accumulating gradually out of countless gentle corrections, the way a slow, steady hand can calm a frightened animal. Van der Meer had turned a statistical insight into a working machine, and without it, Rubbia's collisions would have been far too rare to ever reveal a W. With the antiprotons cooled and the protons accelerated, the two beams could be steered into each other inside enormous detectors built to watch the wreckage. The energy was there, the collisions were arranged, the instruments were ready. All that remained was to look and to recognize the W in the brief, faint signature it left as it died. The looking happened inside two enormous detectors called UA1 and UA2, built around the points where the proton and antiproton beams crossed. A detector like this is a great barrel of layered instruments wrapped around the collision point like the layers of an onion, each layer recording something about the particles that come spraying out when proton meets antiproton. The job was to sift through millions upon millions of collisions, almost all of them ordinary and uninteresting, and find the rare few that had made a real W boson for an instant. You cannot see the W directly, and this is the crucial point that shapes the whole hunt. The W is born and dies far too fast to leave a track or strike a sensor. By the time the detector's innermost layer could register anything, the W is long gone, transformed into the lighter particles it became. So the experimenters were never looking for the W itself. They were looking for the unmistakable pattern of debris it leaves behind, the particular spray of leftovers that only a dying W produces. The W signs its name in what it turns into. Rubbia had worked out exactly what that signature would be. One clean way for a W to die is to turn into an electron and a neutrino, or their heavier cousins. The electron would shoot out sideways from the collision with a large, sharply defined energy, flung clear of the beam. The neutrino, true to its ghostly nature, would slip out of the entire detector without touching a thing, carrying away energy and momentum unseen. So the telltale sign of a W was a single energetic electron flying out one side, paired with a matching amount of energy and momentum that had simply vanished, balanced by nothing. That missing push was the neutrino's invisible footprint. In late 1982 and into early 1983, after sorting through a staggering number of collisions, the teams found a handful of events that fit the pattern exactly. A lone energetic electron kicked out sideways, and a clear imbalance of momentum marking where the unseen neutrino had escaped. The two together adding up to the mass of a heavy parent particle, right around 85 protons worth, just as the theory had promised. The W boson had been caught, not seen but reconstructed, recognized by the precise shape of its dying. The announcement came in 1983, and soon after, the same machine and detectors found the Z boson too, the heavier neutral cousin, identified by its own distinct signature. The electroweak theory, predicted years earlier on the strength of its mathematics, now had its carriers in hand, weighed and confirmed. The unification of the weakened electromagnetic forces had passed its hardest test. The recognition was swift and unusually so. The Nobel Prize in Physics went to Carlo Rubbia and Simon van der Meer in 1984, only about a year after the discovery, a remarkably short wait by the standards of a prize that usually rewards work decades old. The committee was honouring not just the finding of the particles, but the whole feat. The daring collider design and the cooling trick that made it possible, the will and the cleverness together. Glashow, Weinberg and Salam had been honoured for the theory 5 years before. Now the experimenters who proved them right took their turn. So the W was real, weighed and confirmed. But the discovery had only deepened the question we started with. The W existed for so short a time that no clock could ever tick fast enough to time it directly. Its death was not measured with a stopwatch. It was inferred, read out of the very shape of the particle, through a chain of reasoning that begins by rethinking what a particle's lifetime even is. And that is where we turn next, because the W's lifetime is not a fixed span at all. It is a matter of chance. Before we can time the W's death, we have to correct a picture almost everyone carries about lifetimes, the same picture that misled us about dying at the very start. When we say something has lifetime, we imagine a fixed span, a clock that starts ticking at birth and rings at a set time, like a candle of a certain length that burns for a known number of minutes and then gutters out. A particle's lifetime is nothing like that. It is not a countdown. It is a matter of pure chance, the same chance we first met in the irregular clicking of the Geiger counter. Recall that ticking, fast then slow, with no pattern from one click to the next. We can now name what it was telling us. Each radioactive atom in the rock is not running a countdown to a scheduled decay. At every instant, it simply has a certain fixed chance of transforming in the next moment, and whether it does is genuinely random, like a roll of dice. An atom that has sat unchanged for 1,000 years is no more likely to decay in the next second than a fresh one. It carries no memory of how long it has waited. The dice are rolled anew every instant with the same odds each time. This is why a single atom keeps no schedule, while a large sample keeps a faithful average. Any one atom might transform in the next second or might sit for ages, you cannot say which. But take a vast number of them, trillions upon trillions, and the randomness smooths out. A definite fraction of them will decay in any given stretch of time, because with so many dice rolling, the average is rock steady even though each roll is unpredictable. The sample as a whole behaves with great regularity, built entirely out of countless individual events that are each pure chance. From this comes the shape that governs all such decay, called exponential decay, and it is worth picturing plainly. Suppose that in a certain span of time, half of the atoms in a sample will have transformed. That span is called the half-life. After one half-life, half remain. Those survivors have no memory, so in the next half-life, half of them go too, leaving a quarter of the original. In the next, half again, leaving an eighth. The amount left keeps halving, step after step, falling fast at first and then trailing off into a long, thin tail, never quite reaching zero. That steady halving is the signature of memoryless random decay. The half-life, or the closely related average lifetime, is the one number that captures the whole behaviour. It does not tell you when any particular particle will die. It tells you the odds. A short lifetime means the dice are heavily loaded toward decaying soon, so the population melts away quickly. A long lifetime means the odds of decaying in any moment are tiny, so the population lingers. The free neutron's lifetime of about 15 minutes means that, on average, a neutron rolls the right combination to transform after roughly that long, though any individual neutron might go much sooner or much later. So when we ask how long the W boson lives, we're not asking for the length of a fixed candle. We're asking about the odds. We're asking how heavily the dice are loaded toward its decay, how fast a population of W bosons would melt away if you could somehow make many at once. The W's lifetime is the average over countless individual deaths, each one random, each one a roll that came up the same way, become something lighter now. This reframing is what finally lets us put a number on a death too fast for any clock. We cannot time a single W, nothing ticks that quickly, but the chance of decay, the loading of the dice, leaves a mark on the particle itself, written into a quantity we can actually measure. The shorter the average life, the broader and blurrier a certain feature of the W becomes, and that blur is something detectors can read. To understand how a lifetime hides inside a blur, we need one more strange and genuine rule of the quantum world, the trade between time and certainty. The rule we need is one of the genuine strangenesses of the quantum world, and it is a cousin of the famous uncertainty principle you may have heard of. The familiar version says you cannot know both exactly where a particle is and exactly how it is moving. Pin down one and the other goes blurry. There is a second version of the same idea, less often told, that trades time against energy, and it is the one that lets us read a lifetime off a particle that no clock could ever catch. The trade goes like this. To know the energy of something with great precision, you have to watch it for a long time. Give it plenty of time and its energy comes into sharp focus. But if a thing exists only for a fleeting instant, there is simply not enough time to pin its energy down, and its energy becomes correspondingly blurry, smeared across a range rather than fixed at a single value. The shorter the life, the wider the smear. A long-lived thing has a sharp, definite energy. A short-lived thing has a fuzzy one. This is not a flaw in our instruments. It is a feature of the world itself, as real as anything in physics. A particle that lives only briefly genuinely does not have a single sharp energy. It has a spread of possible energies, and the briefer its existence, the broader that spread. Nature refuses to assign a precise energy to something that does not stick around long enough to be pinned. An everyday comparison helps, drawn from sound. Strike a tuning fork and let it ring for a long steady time and you hear one clear pure note, a single sharp pitch. Now strike something that makes only the briefest click, a single tap with no ringing at all. That click has no clear pitch. It is a smear of many frequencies at once, a thud rather than a tone. The longer a sound sustains, the purer and more definite its pitch. The shorter and more clipped it is, the more its pitch spreads into a blur. A very short sound simply cannot have a pure tone, because there is not enough of it to define one. Hold that comparison, then notice where it stops fitting. With sound, the spreading is a fact about waves that we can hear directly, and we tend to think of it as a quirk of acoustics. With a particle, the spreading is a fact about existence itself. The particle's energy is not merely hard to measure when its life is short. It genuinely does not have a single value to measure. The tuning fork at least had a true pitch we struggle to catch in a short click. The short-lived particle has no single sharp energy at all. The blur is the reality, not a limitation on our seeing it. Now connect this to mass, and the door opens. For a particle, mass and energy are the same currency, as we have said. The mass of a particle is just its stored energy when it sits at rest. So if a short life makes a particle's energy blurry, it makes the particle's very mass blurry by the same token. A long-lived particle has a sharp, well-defined mass. A short-lived particle has a smeared mass, a mass that is not one number, but a spread of numbers around a central value, the spread growing wider, the faster the particle dies. This is the bridge we needed. The W boson dies so fast that its mass cannot be sharp. It must be smeared across a range, and the width of that smear is set directly by how brief its life is. We cannot time the W with a clock, but we can measure how blurry its mass is, how wide the smear, and from that width read off the lifetime, because the two are locked together by this trade between time and certainty. The blur is the lifetime wearing the disguise of a mass. The blur in a particle's mass has a name and a number, and once we have them, the W's lifetime is almost in our hands. Physicists call the width of that smear the decay width of the particle. It is exactly what it sounds like. take the spread of masses the particle is measured to have, and the width of that spread, how far it reaches from one side to the other, is the decay width. A long-lived particle has a narrow width, its mass sharp and well-defined. A short-lived particle has a broad width, its mass smeared across a wide band. For the W boson, that width has been measured, and it is large, as befits a particle that dies so quickly. The W's mass is smeared by about 2 billion of the energy units we've been using, the same units in which the W's mass itself is about 80 billion. So picture the central mass of the W sitting at 80 billion units, with a fuzzy band around it about 2 billion units wide. The particle's true mass not a single point but a spread across that band. 2 billion units of blur on a particle whose whole mass is 80 billion is a substantial fuzziness, the unmistakable mark of a particle in a great hurry to be gone. It helps to feel the contrast with something stable. An electron, which as far as we know never decays, has a mass that is sharp to an extraordinary degree, no measurable blur at all, because with an endless life there is all the time in the world to define its energy precisely. A proton, also effectively eternal, is the same, a knife-edge mass with no width to speak of. These long-lived particles wear sharp, single masses. The W, living for the briefest flicker, cannot. Its 2 billion unit width is the price of its haste, written directly into how poorly its mass can be defined. Here is a way to picture what is really being measured. Imagine you could weigh many W bosons, one after another, each one freshly made in a collision, and record the mass of each. If the W were long-lived, every measurement would come back at very nearly the same number, 80 billion units, clustered tight. Instead, the measurements scatter. One W comes in a little heavier, the next a little lighter, spread out across a band about 2 billion units wide, clustering thickest in the middle and thinning toward the edges. That scatter is not measurement error. It is the genuine spread of masses the short-lived W actually has, and the breadth of the scatter is the decay width. This is the quantity detectors can actually get at, which is what makes it so valuable. You cannot start a stopwatch on a W, but you can collect thousands of W bosons, reconstruct the mass of each from the debris it left, plot how those masses scatter, and measure the width of the resulting spread. That width is a direct readout of something no clock could touch. The particle's impatience to decay has been converted into a shape on a graph, a band of a certain breadth, and the breadth is the thing we measure. And because the decay width and the lifetime are two faces of the single trade between time and certainty, knowing one gives you the other immediately. A wide width means a short life, a narrow width means a long one, and the relationship is exact, not approximate. The 2 billion unit width of the W is therefore not just a curiosity about its fuzzy mass, it is the lifetime itself, encoded. All that remains is to turn that width of energy into a span of time, and the number we have been building toward finally falls out. Turning the width into a time is the step where the W's lifetime finally appears as a real number, and the conversion rests on the same trade between time and certainty we have been leaning on. The rule, stated as a relationship, says that the width of a particle's mass and the length of its life are inversely linked. Multiply them together and you always get the same fixed quantity, a constant of nature. So a wider mass means a shorter life, by exactly the amount the constant demands. Know the width, divide it into that constant, and out comes the time. We have the width, about 2 billion energy units of blur on the W's mass. Feed that into the relationship, and the lifetime that emerges is staggeringly small. The W boson lives, on average, about 3/10 millionths of a billionth of a billionth of a second. Written as a span of time in plain words, that is a 3 followed by reaching down through millionths, then billionths again, before you arrive at the digit. It is among the shortest lifetimes ever measured for anything. Let us build that smallness in stages, because a number that extreme means nothing until you climb down to it one rung at a time. Start with a second, the beat of a heart, the span of a single word spoken aloud. divide it into 1 billion parts, and one of those parts is a nanosecond. The time light takes to cross from one side of your hand to the other. Already, that is far quicker than anything your senses can follow. The W's life is not a nanosecond. It is far, far shorter than that. Take that nanosecond and divide it again into 1 billion parts. Now you're in a realm where even the fastest electronics ever built cannot keep up. A slice of time in which light, the quickest thing there is, barely moves at all. The W's life is shorter even than this. You have to go down one more enormous step, dividing yet again, before you reach the span in which the W boson comes into being, exists, and is gone. 3 of those almost unimaginably tiny slices, and the W has lived its entire life. This is why no clock could ever time it directly, and why the whole roundabout path through mass and width was necessary. There is no instrument, and there could be no instrument, that ticks fast enough to start at the W's birth and stop at its death. The fastest measurable processes we can engineer are slower than the W's whole life by a vast margin. The lifetime had to be inferred, read out of the blur in the particle's mass, precisely because it can never be caught by watching a clock. The width on the graph was the only window onto a span of time too brief for timekeeping of any ordinary kind. And notice that this number is not a guess or a rough estimate. It follows cleanly from a measured quantity, the width of the W's mass, through an exact relationship that holds throughout the quantum world. Measure how fuzzy the mass is, and the lifetime drops out with confidence. The 2 billion unit width and the 3/10 millionths of a billionth of a billionth of a second life are the same fact stated in 2 languages, energy and time, each translatable into the other by a fixed rule of nature. So we finally have it, the answer the title points at, in the form of a hard number. The W boson lives about 3/10 millionths of a billionth of a second, but a number that small still floats free of anything we can picture, just digits trailing into smallness. To make it mean something, we need to anchor it to a distance, to ask how far even light, the fastest thing in the universe, can travel in a life that brief. To make that vanishing span of time mean something, tie it to a distance, because distance is easier to picture than time. Light is the fastest thing there is, the universal speed limit, crossing about 300,000 kilometers in a single second. In 1 second, light could circle the Earth more than 7 times. It is the natural yardstick for asking how far anything can get in a given stretch of time. So let us ask the simplest possible question. In the whole life of a W boson, how far does light travel? Take the W's lifetime, that 3/10 millionths of a billionth of a second, and let light run for exactly that long. The distance it covers is almost nothing. Light, in the entire life of a W boson, crosses a distance much smaller than a single atom. It does not get across an atom. It does not get across the tiny nucleus at the atom's heart. It crosses only a fraction of the width of a single proton, one of the particles inside that nucleus, the very particle we used earlier as our standard coin of mass. Sit with how astonishing that is. The proton is already almost incomprehensibly small. You could line up millions of protons across the width of a human hair and still have room to spare. The proton is so small that for most of the history of science no one even suspected it had any size at all. And yet, in the entire lifetime of a W boson, light, the fastest thing in the universe, does not even make it all the way across one proton. It crosses a mere sliver of that already unimaginably tiny distance, a fraction of the width of a single one of the protons that make up an atom's core. This is the truest measure of how brief the W's life is, far better than the string of digits. The lifetime written out is just a number trailing into smallness, hard to hold in the mind. But the distance light travels in that time is something you can almost picture, by picturing how it fails to picture. The fastest thing there is, set loose, and it cannot even traverse one of the smallest objects we know. The W is born, lives, and dies before light can cross from one edge of a proton to the other. There is a quiet consequence buried in this, and it returns us to why the W must be reconstructed rather than seen. A particle that exists for so short a time, in so small a space, can never travel anywhere meaningful before it dies. It cannot fly across a detector and strike a sensor, because it expires before light itself could cross a proton, let alone reach the instruments waiting millimeters or meters away. The W dies essentially on the very spot where it was born, in a region far smaller than an atom, having gone nowhere at all. This is the deepest reason it leaves no track, and why everything we know about it has to be pieced together from the longer-lived particles it turns into. So the answer to our title's question now has both a number and a picture. The W boson lives about 3/10 millionths of a billionth of a second, a span so brief that light, racing at full speed, crosses only a fraction of a single proton before the W is gone. That is the fact. We have measured it, anchored it, and made it as vivid as such a thing can be made. But knowing how short the life is only sharpens the real question, the one the title truly asks. Not how brief, but why. Why does the W die so fast when other particles linger? The rest of our climb is the answer, and it has two parts. The first is that the W simply has too many ways out. The first reason the W dies so fast is that it has too many ways to die at once, too many open doors, and a thing with many exits leaves quickly. Imagine a room with a single narrow door. People trickle out slowly, one at a time, and the room empties at a leisurely pace. Now imagine the same crowd in a room ringed with wide open doors on every wall. The crowd pours out in a rush, because there are so many ways to leave and all of them are available at once. The W boson is the second room. It has many separate ways to decay, all open simultaneously, and that abundance of exits is part of why it goes so fast. Here is the principle beneath the picture, and it is one of the quiet engines of the quantum world. When a particle has more than one way to decay, the chances do not compete or divide a fixed budget. They add. Each available path contributes its own share to the total rate of decay, and the more paths there are, the faster the particle goes overall, because every open door drains the population in parallel. A particle with one way out lives a certain time. Give it 5 ways out, each as easy as the first, and it dies roughly 5 times faster, because all 5 are working at once to end it. The W boson is rich in such doors. It can turn into a whole assortment of different light particles, several distinct combinations, each a separate and legitimate way for it to die. We will lay out the actual menu of these in a moment, but the count is what matters here. Because the W is so heavy, sitting on its great fortune of stored energy, it can afford to become many different things. Each lighter combination it could turn into is within its means, energetically, and so each one is an open door. With so many doors open at once, the W's total rate of decay is high, and its lifetime correspondingly short. It helps to contrast this with a particle that has few options. Recall the free neutron, which lives about 15 minutes. The neutron is only barely heavier than the proton it decays into, so it has almost no stored energy to spend, and essentially one way to go, become a proton, an electron, and a neutrino, and nothing else is affordable. One narrow door, and a long slow trickle out of it. The neutron's poverty of options is part of why it dawdles. The W's wealth of options is part of why it races. Notice that this richness of exits is itself a consequence of the W's great mass, which keeps tying back to the same route. A light particle can become only the very few things lighter than itself, and often there is almost nothing cheaper for it to turn into. A heavy particle, sitting high above a great many lighter possibilities, can become any of them, and so it has many doors precisely because it is heavy. The W's 85 proton mass does not just store the energy that funds its decay, it opens a wide array of cheaper things for that energy to become. But the number of open doors is only half the story, and on its own it would not be nearly enough to explain a life shorter than light crossing a proton. A handful of decay paths might speed things up several-fold, But the W is faster than the neutron not by a factor of a few, but by an almost unfathomable margin. Something else is at work, something far more powerful than mere counting of exits, and it too comes straight from the W's heaviness. Before we reach it, we should look at what is actually on the other side of those open doors, the real things a dying W becomes. Let us look at what is actually behind those doors, the real menu of things a W boson can become, because naming them makes the decay concrete instead of abstract. When a W boson dies, it always turns into a pair of lighter particles, and the pairs fall into two broad families. The first family is a lepton and its neutrino. The second is a pair of quarks. Every W decays one or the other, and which family it lands in, and which member within the family, is the random roll we have been talking about all along. Take the lepton family first, because we have already met its simplest case. A lepton is one of the light fundamental particles that includes the electron and two heavier cousins, the muon and the tau, each with its own matching neutrino. When a W decays this way, it produces one of these charged leptons together with its partner neutrino, an electron and an electron neutrino, or a muon and a muon neutrino, or a tau and a tau neutrino. This is exactly the kind of pairing that signalled the W's discovery, the energetic electron flung out one side and the unseen neutrino carrying off its balancing share. 3 versions of this door stand open, one for each generation of lepton. The quark family is where most W decays actually go, and it is worth meeting quarks plainly. Quarks are the particles that make up protons and neutrons. A proton is 3 quarks bound together, and so is a neutron, in different combinations. Quarks never appear alone in the open. The force that binds them is so strong that the instant a quark is set free, it immediately dresses itself in a spray of other particles yanked out of the surrounding energy, bundling into a tight jet of debris flying in roughly one direction. So when a W decays into a pair of quarks, what the detector actually sees is not 2 bare quarks, but 2 sprays, 2 jets, shooting out back to back. This is why the W's decay shows up in detectors in 2 distinct guises. Sometimes it appears as a clean-charged lepton paired with missing energy, the lepton and neutrino door. More often it appears as a pair of jets, the quark door, 2 showers of particles marking where 2 quarks flew apart and instantly clothed themselves. Reading a W decay means recognizing both signatures, the lone energetic lepton with its invisible partner, or the back-to-back sprays of a quark pair turning into jets. The reason there are so many open doors now comes into focus. 3 lepton pairings, plus several distinct quark pairings, each a separate way for the W to die, all of them affordable because the W is so heavy and sits so far above its products in energy. Add the doors, and you have the abundance we spoke of, the room ringed with exits. The quark doors are the busier ones, taking the larger share of decays, while the 3 lepton doors each take a smaller, roughly equal slice. Together they account for every W that has ever died, and notice the through line to the very first idea of this whole script. The W does not break into pieces of itself. There were never a lepton and a neutrino, or a pair of quarks hiding inside it. They are made fresh in the instant of decay, conjured out of the W's stored mass, exactly as the neutron made an electron and a neutrino it did not contain. The W becomes them, fully and cleanly, paying for their masses and their speed out of its 80 billion unit fortune. The menu is a menu of transformations, not of content spilled. With the doors named and their destinations known, we can finally reach the second and far more powerful reason the W dies so fast. The second reason the W dies so fast is the powerful one, far stronger than the mere counting of doors, and it comes down to a single fact about the weak force. The rate at which the W decays climbs steeply with its mass, rising not in step with the mass but with the cube of it. Cube is the key word. To cube a number is to multiply it by itself 3 times, and that turns a large number into a staggeringly larger one. The W's heaviness does not just open many doors, it drives every one of them open with tremendous force, because the decay rate scales as the mass multiplied by itself 3 times over. Feel what cubing does, because the whole explanation rests on it. Double a length and you double it. Simple. But double the side of a cube and its volume grows 8-fold, 2 times 2 times 2, because volume depends on the cube of the side. A modest increase in the side produces a dramatic increase in the volume. The weak decay rate behaves like that volume. A particle that is 10 times heavier than another, decaying by the weak force, does not decay 10 times faster. It decays roughly 1,000 times faster, 10 multiplied by itself 3 times, because the rate follows the cube of the mass. Now apply this to the W boson, which is enormously heavy by the standards of the particles it competes with for our attention. Its mass is not a little above the lighter particles that also decay by the weak force. It towers over them, and because the decay rate goes as the cube of that towering mass, the W is driven to decay with a violence utterly out of proportion to a particle merely somewhat heavier. The great mass that opens so many doors also slams each one open, with a force that grows as the cube, and the two effects together, many doors and each one fiercely driven, produce a lifetime shorter than light crossing a proton. It is worth being clear about why the rate climbs at all. In plain terms, a heavy particle sits on a great fortune of stored energy, and the more energy there is to spend, the more ways and the more vigorously it can be spent. There are more possible states for the decay products to fly off into, more room in the space of outcomes, when there is more energy to share among them. The weak force gathers all of that up, and the result is a rate that does not merely rise with the mass but accelerates with it, the cube law capturing how steeply the available outcomes multiply as the parent gets heavier. This is the deepest answer to our title's question, and it deserves to be said plainly. The W boson dies so fast chiefly because it is so heavy, and because the weak force punishes heaviness with a decay rate that grows as the cube of the mass. Pile a great mass onto a particle that decays weakly, and you have built something that cannot last, because its very heaviness drives its destruction at a runaway pace. The W's 85 proton mass is not incidental to its short life. It is the direct cause, amplified 3-fold by the cube. We can test this claim, and testing it is the most convincing thing of all, because there exists a particle that decays by the very same weak force, through the very same kind of process, yet lives not for a sliver of a proton crossing, but for a span millions of times longer. If heaviness is truly the cause of the W's haste, then that other, far lighter particle should be far more patient, and by an enormous margin. It is. Meeting it, and seeing exactly why it lingers, will lock the whole argument into place. The particle that proves the point is the muon, and it is the perfect test case, because it decays by the very same weak force as the W, yet lives vastly, almost incomprehensibly longer. The muon is one of those leptons we just met, a heavier cousin of the electron, about 200 times the electron's mass, but still a featherweight next to the W. Muons rain down on you constantly. They are made when cosmic particles from space strike the upper atmosphere, and they sleet through your body, through the ground, through everything, by the thousands every minute. And like the W, the muon is unstable. It decays. The question is how fast. The muon's lifetime is about 2 millionths of a second. That sounds short, and by everyday standards it is. A muon is gone in far less than the blink of an eye. But hold it against the W. The W lives about 3 10-millionths of a billionth of a billionth of a second. The muon lives about 2 millionths of a second. The muon outlives the W by a factor so large it strains the words. The muon lasts something like millions of trillions of times longer than the W boson, though both die by the same weak force. 2 particles, 1 weak interaction, and a gap in their lifetimes wider than almost any comparison in physics. Why such a chasm? The answer is exactly the one we have been building, and the muon confirms it cleanly. The muon decays by emitting a W boson, just as the neutron does, but here is the crucial thing. The muon is far too light to make a real W. It does not have anywhere near the 85 proton mass needed to bring a genuine W into being, so it cannot use a real W at all. it must use a virtual one, that fleeting borrowed courier we met earlier, conjured far below the W's true mass and existing only on the briefest borrowed time before it converts into the electron and neutrinos that fly out. And borrowing a courier so far beyond your means is enormously costly. In the currency of probability, the muon is trying to summon, even virtually, a particle 85 proton masses heavy, while having almost none of that mass itself. Nature permits the loan, but it makes it exceedingly rare, and that rarity is precisely why the muon decays so slowly. The weak force, when it has to work through a virtual W stretched so far beyond its natural mass, becomes the feeble, sluggish thing Fermi first measured. The muon's patience is the weak force showing its true, shy face. The W, by contrast, does not have to borrow anything. It is the heavy courier, already real, already present in full. It does not need to summon a particle beyond its means. It simply is that particle, and it can decay directly, immediately, with no costly stretch. This is the heart of the contrast. The muon decays slowly because it must reach far beyond its mass to borrow a W it cannot afford. The W decays almost instantly because it is the W, free to come apart at once with nothing to borrow and no debt to pay. So the same weak force gives two utterly different lifetimes, and the difference is entirely about mass. The light muon, forced to work through a virtual W far beyond its reach, lingers for millions of trillions of times longer than the heavy W, which pays no such toll. The cube law and the borrowing cost are two views of one truth. Heaviness rushes the W to its end, and lightness grants the muon its long patience. This contrast lets us finally tie together the two strands that have run through the whole story and see that the weak force's feebleness and the W's haste are not two facts, but one. Now the two strands can be braided into one, and it is the quiet climax of the whole story. The weak force is feeble, and the W boson is short-lived for one and the same reason, and that reason is the W's enormous mass. We have been circling this from both sides, and we can now say it plainly and see why it must be true. Feebleness and haste are not two separate properties of the weak force that happen to coexist. They are a single fact about a heavy courier, viewed from two directions. Trace the feebleness first. The weak force is weak in everyday life because its courier, the W, is so heavy. By Yukawa's logic, a heavy courier can be conjured only on the briefest borrowed time and can reach only the tiniest distance, so the force it carries is short-ranged and rare. Worse, in any ordinary process like a neutron decaying or the muon coming apart, the particles involved are far too light to make a real W, so they must borrow a virtual one far beyond their means, and that costly borrowing is exactly what makes the force so faint and so slow. The weak force is feeble because its courier is heavy and almost always out of reach. Now trace the haste and watch it spring from the identical root. When a real W does get made, in a violent enough collision, it is itself that heavy courier, sitting on a vast fortune of stored mass. The cube law means that fortune drives its decay at a furious rate, and its many open doors all pour at once. The W dies almost instantly because it is heavy. The very mass that put the W out of reach for ordinary processes, and so made the force feeble, is the mass that rushes the W to its end the moment it exists for real. So the same number, the W's 85 proton mass, explains both halves. Heaviness puts the courier out of reach, and a force whose courier is out of reach is feeble. Heaviness loads the courier with energy, and the cube law turns that energy into a runaway decay, so the courier is short-lived. One mass, two consequences, pulling in what looked like opposite directions but springing from the same source. The shyness of the weak force in your body, the slow, safe pace of radioactivity, the swift death of the W in a collider, are all the heavy courier seen from different angles. There is a real beauty in this unification, the kind physics lives for. Two facts that seem to have nothing to do with each other, a force being weak and a particle being quick to die, turn out to be the same fact wearing two faces. You cannot have one without the other. A weak force of this kind must have a heavy carrier, and a heavy carrier must be short-lived. The feebleness you feel as safety and the haste we measure as a vanishing lifetime are locked together. Two readings of a single underlying truth about mass. And this is why the title's question has the answer it does. The W boson dies in a sliver of a proton crossing not by accident, and not because of some special fragility, but because it is the heavy carrier of a force whose weakness is the very signature of that heaviness. To ask why the W dies so fast is to ask why the weak force is weak, and they have the same one-word answer: mass. Having understood that, we can return to the experimenter's problem, because knowing why the W dies so fast makes vivid just how hard it is to study something that is never there to be studied. You can never see the W. You can only read its handwriting and what it leaves behind. Because the W dies on the spot where it is born, before light can cross a proton, no instrument ever sees it, and this shapes everything about how we study it. There is no question of catching a W in flight, no track to follow, no sensor it could ever reach while still alive. The W is, from any detector's point of view, never there. It exists only in the vanishing instant between a collision and the appearance of its decay products, a moment shorter than anything an instrument can register. Everything we know about the W is read backward, from the longer-lived particles it turns into. This is less strange than it first sounds, because we reconstruct unseen causes from their effects all the time. You never see the wind, only the bending trees and the scattering leaves, and from those you read the wind's strength and direction with confidence. You never see the past collision on an empty road, only the skid marks and the resting cars, and from those a careful eye rebuilds what happened, how fast, from which direction. The W is studied the same way. It leaves a characteristic scatter of debris, and from that debris its presence, its mass, and even its lifetime are reconstructed. The reconstruction works because the decay products carry the W's signature in conserved quantities. Energy and momentum are never created or destroyed, as we said at the very beginning, so whatever the W had, its decay products must carry between them exactly. Catch the products, measure each one's energy and direction, and add them all up, and you recover the energy and momentum of the parent W that made them, even though the W itself was gone before any instrument could touch it. The debris is a faithful ledger, and the W's properties are written in the totals. There is a clean way physicists use this, called reconstructing the invariant mass. Suppose a W decays into a pair of jets, two sprays from two quarks. Each jet's energy and direction can be measured by the detector. Combine them with the rule that ties energy and momentum to mass, and out comes a single number. The mass of the parent that must have produced exactly that pair flying exactly those ways. Do this for one event and you get one mass. Do it for thousands of W decays and you get thousands of masses, which scatter into that band we spoke of, clustering around 80 billion units, with a width about 2 billion wide. The W's mass and lifetime emerge from the pile of reconstructed events, never from a single sighting. It is worth pausing on how indirect and how trustworthy this is. Not one of the W bosons whose mass appears in that band was ever observed. Each was inferred after the fact from the energies and directions of the particles it left behind. Particles that did live long enough to strike the detector and be measured. The W is a conclusion, not an observation. And yet the conclusion is rock solid, because the bookkeeping of energy and momentum is exact, and the pattern of debris a dying W produces is unmistakable. We are certain of a particle no one has ever seen. But one of the W's two decay families makes this reconstruction much harder, and it is the very family that announced the W's discovery. When the W decays into a charged lepton and a neutrino, one of the two products is neutrino, that ghost which slips through the entire detector untouched, carrying away energy and momentum without leaving a trace. Half the ledger walks out the door unseen. To reconstruct a W that decayed this way, physicists had to find a way to weigh something they never caught, to measure the push of a particle that touched nothing. The trick they use is one of the most elegant in all of detector physics. The trick for catching the uncatchable neutrino rests on momentum, the quantity of motion a thing carries, and on the fact that momentum, like energy, is never lost. Momentum has a direction as well as an amount. A particle flying left carries leftward momentum, one flying right carries rightward, and if the two are equal they cancel, summing to nothing. This bookkeeping is exact and total. Whatever momentum is present before an event must be present after, added up across everything, in every direction. The neutrino cannot escape this ledger even though it escapes the detector. To use it, the experimenters lean on a clever feature of how the collisions are arranged. The protons and antiprotons come in along a single line, the beamline smashing together head-on. Crucially, before the collision, there is essentially no motion sideways, no momentum in the directions perpendicular to the beam. The particles are all moving along the beam, not across it. So by the law of conservation, after the collision the total sideways momentum must also be essentially zero, all the sideways pushes of all the debris cancelling out to nothing, just as they summed to nothing before. Whatever flies off to one side must be balanced by something flying off to the other. Now the detector measures every particle it can catch, and adds up all their sideways momentum, all the leftward and rightward and up and down pushes across the beam. If a W has decayed into a charged lepton and a neutrino, the detector sees the lepton and measures its sideways push perfectly well. But the neutrino has slipped away unseen, carrying its own sideways momentum out of the detector. So when the experimenters add up the sideways momentum of everything they did catch, the books do not balance. There is a lopsidedness, an imbalance, a push to one side with nothing visible pushing back. The sum that should be zero is not. That imbalance is the neutrino's footprint. The amount and direction of the missing sideways push tells you exactly what the unseen particle carried away, because it is precisely the amount needed to make the books balance again. The detector never touched the neutrino, but by noticing the hole the neutrino left in the momentum ledger, it measures the neutrino's sideways push as surely as if it had caught it. Physicists call this missing transverse momentum, transverse meaning sideways, across the beam, and it is the standard fingerprint of any neutrino, or indeed anything else, that escapes a collision unseen. This is exactly the signature that revealed the W in 1983. Recall the telltale event, a single energetic lepton flung out one side, and a matching amount of momentum simply missing, unbalanced. We can now see precisely what that meant. The lepton was caught and measured. The neutrino was not, but its sideways push showed up as the imbalance, the missing transverse momentum pointing back the other way. The two together, the visible lepton and the inferred neutrino, reconstructed the parent W, its energy and momentum recovered from one caught particle and one ghost weighed by its absence. There is something quietly profound in measuring a particle by the hole it leaves. The neutrino touches nothing, yet it cannot hide, because it cannot escape the conservation of momentum that governs the whole event. It takes its share of the push and walks out with it, and the very fact that the remaining push is unbalanced betrays exactly how much it took. We weigh the ghost by the dent it leaves in the books, and once both the visible and invisible products are accounted for this way, the full W can be reconstructed, its mass plotted, and its lifetime read from the width of the resulting curve, the curve we should now learn to read directly. The curve we read is called a resonance, and learning to read it is the final piece of measuring the W, because the lifetime is hiding in the shape of the curve in plain sight. Gather thousands of reconstructed W events, each one giving a value for the parent's mass, and plot them. Along the bottom, the mass. Up the side, how many events came in at each mass. The dots do not all land on a single value. They pile up into a peak, tall in the middle around 80 billion units and falling away on both sides, a smooth hill rising to a summit and sloping back down. That hill is the resonance curve, and its shape tells the whole story. A resonance is a familiar thing once you have the everyday version in mind. Push a child on a swing, and there is one rhythm of pushing that works far better than any other, the rhythm that matches the swing's natural pace. Push at that rhythm and the swing climbs high. Push a little faster or slower, and it climbs much less. Plot how high the swing goes against the rhythm of your pushing, and you get a peak, a summit at the perfect rhythm, falling away on either side as your timing drifts off the mark. A particle being made in a collision behaves the same way. There is one collision energy that makes the W most readily, its natural mass, and energies a little above or below make it less easily, giving the peak. Now the crucial part, the part that carries the lifetime, the width of that peak, how broad the hill is from one slope to the other, is set by how long the particle lives, and we already know why from the trade between time and certainty. A long-lived particle has a sharp, well-defined mass, so its resonance peak is narrow and tall, a thin spike. A short-lived particle has a smeared fuzzy mass, so its peak is broad, a wide hill. The breadth of the resonance curve is the mass blur, and the mass blur is the lifetime. The lifetime is not hidden somewhere off the graph. It is the width of the bump itself. Return to the swing to feel this too, because the comparison holds remarkably well. A well-built swing with a little friction has a very sharp resonance. Only a pace very close to perfect works, and the peak is narrow. A swing dragging heavily through thick air or stiff joints has a broad resonance. A wide range of paces work passably, and the peak is wide. Friction, which steals the swing's motion and ends its ride sooner, broadens the peak. In the same way, the W's swift decay, which ends its existence almost at once, broadens its resonance. A quick end means a wide bump, for a swing and for a particle alike. So when physicists measure the W, they are reading a single curve in two ways at once. The position of the peak, where the hill summits, gives the W's mass, about 80 billion units. The width of the peak, how broad the hill, gives the decay width, about 2 billion units, and through the trade between time and certainty, that width is the lifetime, 3/10 millionths of a billionth of a billionth of a second. Mass and lifetime both read from the same plotted hill, one from where it sits and one from how wide it spreads. This is the elegant end of the long chain that began with a particle too short-lived for any clock. We could not time the W, so we measured the blur in its mass. We could not see the W, so we reconstructed it from its debris, weighing even the neutrino by the hole it left. And all of it comes together in one curve, where the width of a bump on a graph is a vanishing lifetime wearing the disguise of a mass. But reading that curve precisely has lately stirred up an argument, because when different teams measured exactly where the peak sits, they did not all get the same answer. When different teams measured exactly where the W's peak sits, they did not quite agree, and that disagreement is one of the live, unsettled questions in physics right now. So let us look at it honestly. Measuring the W's mass to high precision is among the most demanding tasks in all of experimental physics. The mass is about 80 billion energy units, and the teams are trying to pin it down to within a few units out of that 80 billion. A precision like measuring the weight of a large truck and caring about a difference of a few grams. It takes years of work, enormous numbers of collisions, and exquisite control over every quirk of the detector. For decades, the measurements broadly agreed, settling around a value that fit beautifully with the rest of the electroweak theory. The standard model, the grand framework that contains the W, the Higgs, and all the rest, predicts the W's mass quite precisely because everything in that framework is interlinked. The W's mass is tied to the masses of other particles and to the strengths of the forces. Measure those other things, and the theory tells you what the W's mass ought to be. For a long time, the measured value and the predicted value sat comfortably together, another quiet triumph for the theory. Then, in 2022, a team working with data from a now retired American collider, an experiment called CDF, announced a new measurement of unprecedented precision, the most careful weighing of the W ever attempted. And it came in high. Their value for the W's mass sat noticeably above what the standard model predicts, and above what other experiments had found, by an amount far larger than their stated uncertainty. It was not a small drift. By their own careful accounting, the gap was too big to be a fluke, which meant either the measurement had a subtle flaw not yet found, or the theory itself was missing something. This is the kind of moment that makes physicists both excited and cautious, and it is worth honouring both feelings. If the high value is right, it could be a crack in the standard model, a hint of some new particle or force subtly tugging on the W's mass, the first solid sign in years of physics beyond the framework we have. That would be thrilling. But a single measurement, however careful, that disagrees with many others is exactly the situation where caution is wisest, because the history of physics is full of striking anomalies that later prove to be unnoticed errors rather than new discoveries. And the picture is genuinely mixed, which is the honest thing to say. Other experiments, including careful measurements at Europe's Large Hadron Collider, have weighed the W and landed closer to the standard model's prediction, not at the high value the American team found. So the measurements do not all line up. Some sit where theory expects, one sits clearly above. They cannot all be exactly right, and at present no one knows for certain which to trust, or whether some subtle effect is throwing one or more of them off. The tension is real and unresolved. This is what an open question actually looks like, and it is worth seeing plainly rather than tidied up. The W boson, discovered 40 years ago, its lifetime read cleanly from the width of a curve, still holds a mystery in the precise value of its mass, a mystery that may be a measurement quirk or may be a doorway to new physics. We do not yet know. More measurements are underway, and in time the tension will likely resolve one way or the other. For now, the honest statement is that the W's exact mass is contested, and the disagreement is being taken seriously. Leaving that question open, we can step back from how we measure the W to where it came from, in the first instance of the universe when it was not heavy at all. To see the W in its strangest light, go back to the very beginning, to the first tiny fraction of a second after the universe began, because there was a time when the W boson had no mass at all. Everything we have built rests on the W being heavy, 85 protons worth, and on that heaviness coming from the Higgs field filling all of space. But the Higgs field was not always switched on the way it is now. In the universe's first instance, conditions were so extreme that the field had not yet settled into the state that gives particles their mass, and before it settled, the W was weightless, exactly like the photon. Picture those first moments. The universe was unimaginably hot and dense, packed with energy beyond anything that exists anywhere today. In that furnace, the Higgs field was not the steady mass-giving syrup we described. It was roiling, unsettled, like water too hot to freeze into any fixed form. With the field in that state, nothing dragged through it, and so the W and Z bosons carried no mass. They were massless couriers racing at the speed of light, indistinguishable in their reach from the photon. In that earliest era, the weak force and the electromagnetic force were not two different forces at all. They were truly one, the single electroweak force the theory describes, all its carriers alike and weightless. Then the universe expanded and cooled, as a hot gas cools when it spreads, and at a certain moment the Higgs field settled, like our toppled pencil finally choosing a direction, like steam condensing into water as the temperature falls. Physicists call this moment the electroweak transition. In that instant, spread across the whole young universe at once, the field switched on into the mass-giving state it holds today. The W and Z suddenly found themselves dragging through it, and they became heavy, gaining their enormous mass in effect all at once. The photon kept gliding through untouched and stayed massless. That single event split one force into the two we know. Before it, the electroweak force was unified, its carriers all weightless and far-reaching. After it, the W and Z were heavy, and their force became short-ranged and feeble. The weak force, while the photon stayed light, and its force stayed long-ranged, the electromagnetic force. The familiar difference between electricity and the weak force, the difference that puzzled us so deeply that it took 3 physicists and a strange field to explain, was not built into the universe from the start. It was frozen in at one moment, when the Higgs field settled and handed out mass to some carriers and not others, so the W's heaviness, the root of everything in this story, has a birthday. It is not an eternal fact, but a consequence of the universe cooling past a certain point very early on. Before that point, the W was a weightless, long-lived, far-reaching particle, a true twin of the photon, and there was no weak force distinct from electromagnetism. After it, the W was the heavy, short-lived, short-ranged courier we have spent this whole time understanding. The swift death we set out to explain only became possible once the Higgs field switched on, because only a heavy W dies fast, and the W was not always heavy. There is a quiet wonder in this, that the rules we treat as fixed were once different, set into their present form by the cooling of the early universe. The weak force's feebleness, the W's haste, the very distinction between two of nature's forces, all date from a single early moment, and that feebleness, frozen in so long ago, turns out to matter enormously for us, in a way that touches the light and warmth falling on you right now. Because the same weak force, working through a momentary virtual W, is what sets the gentle, patient pace at which the sun burns. The same weak force that rushes the W to its death sets the gentle, patient pace at which the sun burns, and this is where the whole story comes home to something you feel every day: sunlight. The sun is powered by fusion, the joining of light nuclei into heavier ones deep in its core, where the pressure and heat are immense. The very first step of that fusion, the one that gets everything else going, depends on the weak force, working through a fleeting virtual W exactly like the one in beta decay. And because the weak force is so feeble, that first step is extraordinarily slow, which is the best thing that could possibly happen for us. Here is the step. In the sun's core, the basic fuel is protons, the nuclei of hydrogen, the simplest and most common atoms. For fusion to proceed, 2 protons must come together, and one of them must turn into a neutron, so that they can bind into a heavier nucleus, and start the chain that ultimately makes helium and releases energy. But turning a proton into a neutron is a weak force process, the mirror of the beta decay we began with, and it runs through a virtual W. 2 protons must not only collide despite their mutual repulsion, but in the brief instant of contact, the weak force must act, through a borrowed W, to flip one proton into a neutron. That weak step is the bottleneck, and it is a tremendous bottleneck because the weak force is so feeble. 2 protons in the sun's core can collide countless times, bouncing off each other again and again over enormous stretches of time without the weak step ever happening. On average, a given proton in the sun waits billions of years before it successfully fuses, because the weak interaction needed to start the process is so rare, so reluctant, so shy. The sun is not burning fast and bright and brief. It is smouldering, almost grudgingly, held to a crawl by the feebleness of the weak force at its very first step. This slowness is the reason the sun has lasted, and the reason you are here to feel its warmth. If the weak force was strong, if that first fusion step happened readily, the sun would have consumed its fuel in a brief furious blaze and burned out long ago, far too quickly for life to arise on any world around it. Instead, the weak force's reluctance stretches the sun's life across billions of years, a slow, steady burn that has held nearly constant for the whole long span it took for life to appear and evolve on Earth. The same feebleness that makes the W so hard to make, and that we trace to its great mass, is what gives the sun its patience and gives us our time. And feel the thread running all the way back. The sun's slow burn depends on a virtual W, conjured for an instant far below its true mass, exactly as the muon must conjure one to decay, exactly as the neutron does. The weak force is feeble there for the same reason it is feeble everywhere. Its courier is too heavy to make for real, so ordinary matter must borrow it virtually, at great cost in rarity. The W's great mass, which rushes it to its death in a collider, is the very same mass that makes the weak force shy in the sun, and so makes the sun burn slowly enough to warm a living world. So the haste of the W and the patience of the sun are astonishingly the same fact once more, the heavy courier seen from yet another angle. The particle that dies in less time than light takes to cross a proton is the particle whose heaviness keeps our star alight for billions of years. With that connection in hand, we can return at last to the question we started with and answer it in the plainest words. We began with a soap bubble, there one moment and gone the next, too quick to follow, and we asked why a particle deep inside matter should die even faster, in less than a millionth of a billionth of a billionth of a second. We have built the whole answer, piece by piece, and now we can say it plainly, in the simplest words, the way we promised at the start. The W boson dies so fast because it is heavy. That is the answer, stripped to its core. Its great mass, about 85 protons packed into a single particle, is a vast store of energy, and nature spends a large store quickly into many lighter pieces flying free. The mass opens many doors at once, each a different way to decay, and the weak force drives every door open with a rate that climbs as the cube of that mass, so heaviness rushes the W to its end with overwhelming force. A heavy particle that decays by the weak force cannot last, and the W is the heaviest such courier there is. It dies in a sliver of a proton crossing for one reason: it is heavy. And we found that this single fact, the W's heaviness, explains far more than its haste. It is why the weak force is feeble, because a courier so heavy can almost never be made for real and must be borrowed at great cost. It is why the weak force is short-ranged, trapped inside the nucleus by the same logic of mass and reach. It is why the sun burns slowly enough to give us billions of years of steady warmth, because that feebleness throttles the first step of fusion to a crawl. The death of the W, the weakness of the force, the patience of our star, are all one fact seen from different sides. A courier made heavy when the Higgs field switched on in the young universe. Step back and feel the shape of what that means. The forces that govern your world were not fixed from the beginning. There was a moment in the universe's first fraction of a second when the W was weightless, and the weak force did not exist as a thing apart, when it and electromagnetism were one. The universe cooled, a field settled, and mass was handed out, and in that instant the weak force became feeble, and the W became swift to die. The light and warmth on your skin right now are meted out by that frozen-in feebleness, the sun smouldering slowly because of a choice the universe made long before there were stars. So the W boson, dying in a flash too brief to time, never seen but only reconstructed from the debris it leaves and the holes it leaves in the books, turns out to be woven into the most ordinary thing there is, a sunny day. The same heaviness that ends the W almost before it begins is the heaviness that keeps our star alight long enough for a world to grow living things that could one day build machines to catch the W in the act of dying and ask why it dies so fast. The answer, it turns out, is the reason they were there to ask at all. That is the quiet marvel of it. A particle's haste, measured in the width of a bump on a graph, reaches all the way out to the pace of sunlight and the length of our days. The invisible and the everyday are the same story told at two scales. The W dies fast because it is heavy, and because it is heavy, the sun is patient, and because the sun is patient, we are here. Nothing in that chain is loose or decorative. It is all one fact and you live inside it.